Fire on board an aircraft is fortunately a very rare occurrence, considering the potential hazards of a machine carrying and burning large quantities of volatile combustible liquid, either aviation gasoline, avgas, or jet fuel, and having a large, complex, and often heavily loaded electrical system. It is thanks to the technology developed and improved over the years that the current level of fire protection allows passengers and crew to travel in safety. Manufacturers are required to build in fire and smoke detection and suppression systems to cover engines and certain cabin and cargo areas, and include in the aircraft manuals full directions for their operation and use. These procedures will be included in the checklists, and crews need to be well practiced in both normal and emergency drills. The nature of the drills will be largely determined by whether the aircraft is airborne or on the ground, and if on the ground, whether it is moving or stationary, empty or full of passengers, close to other aircraft, or isolated. On the airfield, of course, the crew can call through ATC on the aerodrome fire services for assistance. Larger airfields will even have a radio frequency, usually 121.6 MHz, 1 point up from the emergency frequency 121.5, for direct communication between aircraft and fire crew once they are in attendance. In the air, reliance is placed on either automatic or crew-operated systems, as most areas, other than the flight deck and cabin, or freight bay for cargo aircraft, will be inaccessible. The drills for most aircraft will be similar in concept, but obviously with individual type differences. For most turbine engines, both jet and turboprop, engine fire warnings will be provided by a fire wire, routed around the engine nacelle, to sense abnormal temperature increases in critical areas, such as could be caused by a hot gas leak from the engine. On receipt of a fire warning, the actions would typically be to reduce the minimum power, select the fuel high pressure cock to off, or for a turboprop, the condition lever to feather, and pull the appropriate fire control handle. These actions will isolate the engine from its fuel supply and close off the hydraulic, pneumatic and electrical systems associated with that engine. At the same time, the fire extinguisher squibs will be armed, and if the warning persists, the pilot would select a fire extinguisher to be discharged into the engine. If, after 30 seconds, the warning is still there, the second extinguisher will be selected. If the warning persists after both extinguishers have been used, land as soon as possible. A sensible course of action in any case. The fire drill for most piston engines would involve closing the throttle, feathering the propeller, thus stopping the engine, and isolating the fuel supply by moving the mixture to idle cutoff. Subsequent actions would include turning off the fuel selector and ignition on the affected engine to isolate possible sources of combustion. Although it is still an unusual occurrence, fires in the cabin area and on the flight deck happen more often than engine fires. Most are likely to be caused by overheating or short circuits in electrical or electronic equipment, particularly in the galley, or illegal smoking. Prompt action to identify and isolate the cause of the overheat will usually prevent it developing into a full-blown fire requiring the use of extinguishers. Currently, there are 2 handheld portable fire extinguishers approved for use within the aeroplane cabin. One extinguisher contains an agent called Halon 1211, and the other contains water glycol. The Halon extinguisher is coloured green, and the water glycol is coloured red. And it is very important that flight deck and cabin crews know which to use, and are familiar with the hazards of using certain extinguishers in confined spaces. There are regulations governing the number and location of handheld extinguishers. There should be sufficient to ensure adequate availability, depending on the number and capacity of passenger compartments, the locations of galleys, toilets and other compartments accessible to the crew, and the need to minimize the hazards of concentrations of toxic gas. The table on the screen shows the correlation between passenger numbers and extinguishers. Where the maximum approved passenger seating is at least 31 and not more than 60, at least one portable extinguisher must be Halon 1211. And where the maximum approved passenger seating is 61 or more, at least two must be Halon 1211. The flight deck extinguisher must be Halon 1211. For your information, the lesson includes the latest classification of fires, matched with appropriate extinguisher types. Class A consists of fires involving wood, paper, cloth, and rubber. Class B is for fires of flammable or combustible liquids, such as petrol, kerosene, paint, thinners, etc., but not alcohol or cooking oil. Class C is for fires of flammable gases, such as propane or butane. Class D involves flammable metals, such as magnesium and lithium. The extinguisher that is suitable for electrical equipment, computers, copiers, etc., is not allocated a class letter, but is recognized by the electrical flash symbol. Class F is for fires involving cooking oils and fats, olive and maize oils, butter, lard, etc. Note that the extinguisher categories do not include halon or BCF, which is banned for general use, but which is exempted for aviation and military use, and a few other special applications. Fire detection systems can be fitted in various locations in aircraft, where monitoring by the crew is either not possible or not practical. They work by detecting either heat or smoke. Heat detectors use increases in heat to produce a physical change in a material, altering the conductivity of an electrical circuit, and thus triggering a warning on the flight deck, either visual, audible, or both. Circuits can either be resistive or capacitive. This is the principle used in the engine bay firewire mentioned earlier, and would be used in remote areas such as auxiliary power units and wheel wells. There are two types of firewire detection systems, operating on the principle of their core material having either a negative coefficient of resistance or a positive coefficient of capacitance. The firewire system, which uses the core material having a negative coefficient of resistance, will use direct current, and if it relies on the core having a positive coefficient of capacitance, it will use an alternating current system. Smoke detection systems involve one of two methods. The first uses an electro-optical sensor, which detects a reduction in voltage across a photoelectric cell caused by the interruption of a beam of light by smoke. The second method is the ionized gas system used in domestic smoke detectors, in which the presence of the ionized gas produced by combustion is sensed by the detector cell. These smoke detector systems would be used in internal areas like the freight and baggage compartments, equipment bays, and the cabin toilets. All smoke detectors can be tested prior to flight. The cabin toilets are fitted with an automatic fire extinguisher, which will activate automatically on reaching a predetermined temperature, and the discharge is directed towards the tissue receptacle. It is worth noting that the smoke detector in the toilet is not associated with the fire extinguisher. The saying goes that there is no smoke without fire, and taking the proverb literally, while this may not always strictly be true, it is a reasonable assumption. However, the effects of smoke can be a lot more far-reaching in several ways than the cause of the smoke itself. Smoke can fill an enclosed space remarkably quickly, and, in extreme cases, reduce visibility to nil. Obviously, this would not be good in the cockpit, as the pilots need to be able to see what they are doing, and the extra workload of coping with the problem could cause serious problems at a critical stage of flight. Thorough training and regular and frequent practice of the appropriate emergency drills in the simulator, backed up by a sound knowledge of the aircraft systems, are the best way to combat these types of problems. Crews are provided with oxygen masks and goggles, which will be used in conjunction with the oxygen system, which in these circumstances would need to be set to emergency to provide a positive pressure in the mask to prevent the ingress of smoke or fumes. Protective breathing equipment is covered in more detail later in the lesson. The physiological effects of smoke are initially to cause irritation in the eyes, throat and lungs, and overstimulation of nasal passages, causing coughing and streaming of the eyes and nose. Dense smoke will reduce the lungs' ability to absorb oxygen, resulting in hypoxia, and ultimately asphyxiation and death. It is sobering to recall that, in the Manchester 737 accident of 1985, where a serious wing fire due to a fuel tank breach after an uncontained engine failure on the takeoff roll spread to the fuselage, most of the 55 fatalities were due to inhalation of smoke. In this case, the situation was exacerbated by delays in evacuation, and the fact that as the fire took hold in the rear of the cabin, the burning seat cushions were giving off dense toxic smoke containing cyanide. This accident gave rise to a change in the regulations concerning cabin furnishing materials and flameproofing. Smoke in the cabin, be it from a technical problem or from illegal smoking, can understandably cause grave concern and even panic amongst passengers. As on the flight deck, good training for the situation and calm teamwork by the cabin crew will play a decisive role in coping with the problem. In these circumstances, it is necessary to keep the captain informed, so that he, in turn, can let the passengers know what is happening. Brake overheating is a problem which is only likely to occur either after a rejected takeoff or a high mass landing in marginal field-limited conditions. The actual heating effect is a factor of the aircraft's mass and the rate of deacceleration required. Performance graphs will normally include one for VMBE, or brake energy limit, the maximum speed from which a stop can be safely accomplished within the energy capabilities of the brakes. The energy expended in stopping the aircraft can generate a huge amount of heat. You may have seen this effect if you watch motor racing, with brake discs glowing red under hard braking for a corner. An aeroplane, however, unlike the racing car, will not have any significant cooling airflow during taxiing, and the brakes will remain hot for some considerable time, with the temperature possibly peaking some while after the landing, with the risk of the increase in tyre pressure thus caused exploding the tyre. Again, there will be a performance chart for calculating brake cooling time. No takeoff should be attempted before the expiry of this time, even if the brakes seem undamaged. In extreme cases, the brakes may fade in use, smoulder, or even catch fire, also igniting tyres, or cause tyres to burst, seizing the brakes, and again possibly causing tyre bursts. With these factors in mind, if the aircraft is taxiable after hard braking, a fire vehicle should be in attendance. On VHF frequency 121.6 if available, and the aircraft taxied slowly using other means of retardation if possible, namely reverse thrust or pitch. Consideration should also be given as where to park, that is, not close to buildings, other aircraft, refueling points, etc. Passenger exits furthest away from the undercarriage should be used, and ground personnel kept well away from the landing gear, particularly abeam the wheels, which could, as described earlier, explode with the temperatures and pressures generated by the heavy braking. With regard to fire and smoke protection, certain safety equipment is required. For aeroplanes, pressurized or unpressurized, and having a maximum takeoff mass of over 5,700 kilos, or a passenger capacity of more than 19, each flight crew member must be provided with protective breathing equipment, PBE, which protects the eyes, nose and mouth, and provides oxygen for at least 15 minutes. Enough PB sets must also be carried for each cabin crew member, and will be stowed at the crew stations, with an extra set adjacent to the fire extinguisher stowage. Where there is a cargo area, a PBE must be located outside the cargo bay, but adjacent to the entrance. Normal communications must be possible whilst using PBE. Aeroplanes having a maximum takeoff mass of over 5,700 kilos, or a passenger capacity of more than 9, must be equipped with a crash axe or crowbar stowed on the flight deck. If the passenger capacity is over 200, an additional crash axe or crowbar must be carried, stowed in the rearmost galley. Such axes or crowbars must not be stowed visible to passengers. Smoke, fire, or fumes on board an aircraft are perhaps the most frightening emergencies that can be faced by crew and passengers. Some problems, such as overheated brakes, can be avoided by sound planning and good airmanship. Other emergencies can happen without warning, but with thorough training and familiarity with the equipment, and frequent practice of the emergency drills, a crew will be able to cope with the problem promptly and efficiently, and keep their passengers informed and calm.